Good morning, my dear students. My name is Dr. KCH Apparao, working as an associate professor in mechanical department. So today my topic is radiation heat exchange between gray surfaces. So in last class, we already discussed radiation and a gray surface. We already saw different surfaces, just like black surfaces and gray surfaces. We already discussed the properties of the gray surface. Case of the gray surfaces, we will see only absorption and reflection. There is no transmission. Okay. Uh, so last class also we discussed what is radiation, what is irradiation. So what is radiosity also. Radiation, we know that it is the number of photons that are being emitted by single source. So it is represented by Q, rate of heat transfer in a particular surface, rate of heat transfer between any two surfaces. We know that is represented by Q. Irradiation is the just like one where the radiation is falling on a surface. Suppose the radiation is falling on the surface, it is represented by G. So some portion will be absorbed by this gray surface, some portion will be reflected. So reflecting energy or reflecting energy. So due to this absorption, the surface emits the energy, that is emitting energy, EV. So the addition of these two, rosy and EV, it means reflecting energy and just like emitting energy. So both are called radiosity. So the radiant flux leaving emitted and reflected. So by a surface per unit area, that is called radiosity. So we already discussed the relationship between these radiation and irradiation and radiosity also. We derived the formulas also. You know that so Q, rate of heat transfer is equal to radiosity minus irradiation. You know the formulas. So based upon this one, we discussed this one. Just like these are the epsilons. Epsilon. Okay. Epsilon. Okay. So the finally we got the formula, that is Q is equal to EB minus emitting energy minus radiosity by surface resistance, 1 minus epsilon by epsilon. So it is called surface resistance. Q. Consider this surface resistance is equal to 1 minus epsilon by epsilon. You know this one. Okay. So we already saw the electrical analog formula. So this is, you know, that surface resistance. This is the electrical analog formula. This one is the emitting energy to radiosity. So this one is 1 minus epsilon by epsilon. So this is the surface resistance. This is the just like energy differences. Energy means emitting energy and radiosity. So we already discussed this one. So but in case of black body, so this is different. But in case of black body, if the surface is black body, this is the radiation G. What are the energy falling on the surface that completely absorbed by the surface? So it means there is no reflectivity. Only here we will see absorptivity. So you know that in case of this one, so radiosity is equal to completely emitting energy. So EB is equal to J. We'll see later also. First of all, we'll see the gray surfaces. So this one already we discussed in previous class also, just like uh, uh, radiation energy is compared with the electrical energy. You know that this is the current energy, so electrical energy. So it is compared with the rate of heat transfer, heat energy. So this is one is the resistance. We will see resistances in electrical energy. Here also we will see the surface resistance. Two types of resistances here. Here we can see one is the surface resistance, another one is the space resistance. If you consider both two surfaces, so one surface resistance, that is 1 minus epsilon 1 by epsilon 1. So this one is the 1 minus epsilon 2 by epsilon 2. So this is the surface resistance. This is the surface resistance of the first surface. This is the surface resistance of the second surface. Okay. So one more thing we will see, J1. This is called space resistance. So between the two surfaces. So that is called 1 by A1 F12 view factor F12. You know this one. So this is called space resistance. So and then potential difference. Here voltage difference we will see. Here energy differences. Emitting energy minus radiosity. For particular surface, only one surface. If you consider only one surface, and J1 minus J2, radiosity 1 minus radiosity T 2. So if you consider two surfaces, net exchange between surfaces, here net energy leaving the surface. If you consider one surface, we have to apply these things. If you consider two surfaces, you have to apply these things. We already discussed in previous class also. Just like if you consider this is the one surface, this one is the another surface. So here first we will see the surface resistance. So first emitting energy EB1 will be comes from the surface. Then surface resistance 1 minus epsilon 1 by epsilon 1. Then it will be converted into radiosity. Okay. So similarly for this surface, if you consider this is the temperature of T1, temperature of T2, emissivity epsilon 1, emissivity is equal to epsilon 2. If you consider these things, and so here also just emitting energy EB2, and we will see surface resistance. You see surface resistances. So this is the surface resistance. So this one is the 1 minus epsilon 2 by epsilon 2. Then we get the radiosity 2. Okay. So then we will see the space resistance. This is called space resistance between the radiosity 1 and radiosity 2. So this one is if you consider heat transfer from the surface 1 to surface 2, then this one is the 1 by A1 into F12. So view factor 1 to 2. So this is called space resistance. So this is the radiosity 1, radiosity 2. So we'll see totally if you consider the heat exchange or the rate of heat transfer from the surface 1 to surface 2. Here we'll see three types of resistances. One is the first surface resistance 1 minus epsilon 1 by epsilon 2. Second surface resistance 1 minus epsilon 2 by epsilon 2. Okay. So between the two surfaces, we'll see one more resistance, so that is the surface resistance 1 by A1 into F12. So we have to consider all these things for finding the just like rate of heat transfer from surface 1 to surface 2. We'll see one thing. So here just so we'll see just we are considering two surfaces. So surface 1 and surface 2. So surface 1, temperature of the surface 1 is equal to T1. emissivity of the surface 1 is equal to epsilon 1. So we can say it is represented by 1, that shows surface 1. So another surface, second surface, temperature is equal to T2 and emissivity is equal to epsilon 2. Okay. So first of all, we'll see energy emitting from the surface. So EB1, emitting energy. We can find this one by the help of Stephen Boltzmann. You know that formula, sigma into T1 to the power of 4. You know that. So EB1 is equal to sigma into T1 to the power of T1 to the power of 4. Then we will face the just surface resistance. So 1 minus epsilon 1 by epsilon 1. So by the effect of this surface resistance, so the emitting energy will be converted into radiosity. So that is represented by J1. Okay. J1 here, J1. Similarly, surface 2. So surface 2, EB2 is the emitting energy from the surface 2. So we can EB2 is equal to, according to Stephen Boltzmann, sigma into T2 to the power of 4. This is the value. Then we have to consider the surface resistance. So second surface resistance. So that is the 1 minus epsilon 2 by epsilon. Then it will be converted into just like radiosity. Then the difference just here, between the radiosity 1 and radiosity 2, we will consider the space resistance. Space between the surface 1 and the surface 2. So you know that space resistance is equal to 1 by A1 into F12. If you consider radiation energy transmitting or heat exchange from the surface 1 to surface 2, then we will consider area of the first surface and the view factor from 1 to 2. Okay, this is the space resistance. Then we will find the rate of heat transfer by radiation from surface 1 to surface 2. Then the final equation, you know that electrical analog formula, if you consider this electrical analog formula, first of all, electrical analog formula means EB1, emitting energy. So next surface resistance. So it means 1 minus epsilon 1 by 1 minus epsilon 1 by epsilon 1. Okay. So next to this is the J1, space resistance. Space resistance is equal to 1 by A1 into F12. So from surface 2, okay, here just like another surface, this is the surface 2 resistance. So you know that 1 minus epsilon 2 by epsilon 2. Okay, sorry. So this is the space resistance. Space resistance. This one is a J2, radiosity. Then this is the space resistance of surface 2, 1 minus epsilon 2 by epsilon 2. Then this is the EB2, emitting energy of the body 2. So this is the EB1. So finally the formula is equal to, it means rate of heat transfer from surface 1 to 2 is equal to initial energy minus final energy by total resistance. You know the formula, just like EB1 minus EB2 divided by 1 minus epsilon 1 by epsilon. If you consider the area of the surface 1, then A1 into 1 minus epsilon 1 by A1 into epsilon 1 plus space resistance 1 by A1 into F12 plus 1 minus epsilon 2 by A2 into epsilon. So this is the final formula. So we have to consider all the just radiations, resistances. We'll see this one also. So you know that this is the In case of shape vector, just we already discussed this one. So Q net is equal to A1 F1 to J1 minus A2 F2. Okay. So you know that A1 F1 is equal to A2 F2 according to just like view factor formulas. You know that one. Anyone, you can take anyone. Just to have to consider this one A1 F1 to. Okay. So Q net is equal to A1 F1 to J1 minus J2, just like Q net is equal to J1 minus J2 by A1 F1 to. So this is the just like Q net with respect to radiosities. With respect to radiosities, here you will see we will consider only uh, space resistance. This is called space resistance. Okay. So next we already discussed this one in previous class, previous slide also. Okay. You will see this. This is the radiation between the two surfaces. Already discussed this one. So first surface, temperature of the first surface is equal to T1. Emissivity is equal to epsilon 1. Similarly, surface 2, temperature is equal to T2. Emissivity is equal to epsilon 2. So this is electrical analog formula because first surface has surface resistance, that is called 1 minus epsilon 1 by epsilon 1 if you consider the area A1 into epsilon 1. Then radiosity J1. So next here surface 2. The surface 2 resistance is equal to 1 minus epsilon 2 by A2 into epsilon 2. This is called surface resistance. So resistance of surface 2. So then this is the radiosity J2. Then the radiation, it means surface resistance between the radiosity 1 and radiosity 2. That is the space resistance 1 by A1 into F12. Okay. This is called space resistance. Then the final formula, just like Q net is equal to. So EB1 minus EB2, like electrical analog formula, initial energy, this is the final energy, resistance 1, resistance 2, resistance 3. So energy differences by total resistance, that is the formula. EB1 minus EB2 by 1 by epsilon 1 by A1 into epsilon 1 plus 1 by A1 F12 plus 1 by epsilon 2 by A2 epsilon 2. So this is the formula. You know that EB1 is equal to, according to Stephen Boltzmann law, sigma into T1 to the power of 4. This is EB1. EB2, emitting energy for the black body 2, is equal to sigma into T to the power of 4. Okay. So in which just like sigma is the common, so sigma into T1 to the power of 4 minus T2 to the power of 4. Okay. So these are the epsilon 1, epsilon 2 and epsilon 2. Okay. So then total resistances, resistance of the surface 1, resistance of the space resistance, resistance of the surface 2. All these resistances, how to construct this one. Okay. So then just if you multiply this one A1 by A1, A1 by A1. So then here A1 will be cancelled. Here A1 means A1 by A2 will get. So it means sigma A1 into T1 to the power of 4 minus T to the power of 4 by 1 minus epsilon 1 by epsilon 1. A1 cancel here. So here also A1 by A1 will be cancelled. So 1 minus F12, 1 minus epsilon 2 by epsilon 2 into A1 by A2 will get. So this is the final formula for the rate of heat transfer between the two surfaces. Between the two surfaces, you have to remember this one. By using this formula, you can derive the different conditions. Just like we'll see one more condition. So this is the one more condition. Suppose a small body is placed in a big enclosure. Suppose you can assume this one, one small body and just a big room. So compared to this small body, this big room is very huge difference is there. So we can assume that one for the small body we can consider the temperature T1 and epsilon 1 emissivity is equal to epsilon 1 and the area is equal to A1. Okay, so compared to the small body, big enclosure means the area of the big enclosure we can assume that one, that is the A2 is equal to infinity compared to small bodies. Okay, so no need to consider the area 2 because big enclosure. So in this case, what is the final formula? What is the rate of heat transfer? So how to find the rate of heat transfer between the small body and big enclosure? So we'll derive that formula also. Q12. It means rate of heat transfer from the small body to big enclosure. So this is the formula, this one. According to previous formulas, that rate of heat transfer between the two surfaces, 1 minus sigma A1 into T1 to the power of 4 minus T2 to the power of 4 by 1 minus epsilon by 1 minus epsilon 1. So 1 by F12, 1 minus epsilon 2 by epsilon 2. Okay. So this is the formula we already derived in the previous class, just like previous slide. Okay. So we can take that one. So here just like condition is equal to that area A2 is equal to infinity. So then this total term will be 0. Then the formula will be like this one. And we already discussed the space factor or view factor between the just like a small body and big enclosure. According to that one, yeah, F12 is equal to just like 1. This is the value. That we already discussed. We already covered in previous class also. Then the final formula will be like this one, just like Q12 is equal to sigma area A1 into T1 to the power of 4 minus T2 to the power of 4 by. So 1 minus epsilon. So that 1 minus epsilon 1 by epsilon 1 means 1 by epsilon 1 minus 1. So this just have written like this one. Then that F12, the value of F12 is equal to plus 1. Then A2 is the infinity. If the A2 value is equal to infinity, the total term will be 0. So this is the 0. So then minus 1 plus 1 will be cancelled. Then epsilon comes into numerator position. Then the final formula is like this one. So epsilon 1 into sigma into A1 into T1 to the power of 4 minus T2 to the power of 4. So it means in the case of heat transfer by radiation from small body to big enclosure, just you can use this formula. Q12 is equal to sigma into area into epsilon 1 into T1 to the power of 4 minus T2 to the power of 4. So this is the formula. That. So sigma is equal to Stephen Boltzmann area. A1 is equal to small body area. Epsilon is the emissivity of the small body, and T1 is the temperature of the small body, and T2 is the temperature of the enclosure. So atmosphere, anything you can big enclosure. So this is the formula. So this is the one more case. We'll see another cases also, just like so. Now we'll see the heat transfer between two infinite parallel planes separated by just like small distance. We'll see this one. These are the infinite parallel plates. So infinite parallel plates means we can assume this one area, both are areas of the both surfaces are equal. So area for first surface is equal to A, and the second surface is also A, because infinite parallel plates. So we can assume that areas are same. Then emissivity of the first surface is equal to epsilon 1. Emissivity of the second surface is equal to epsilon 2. Okay. So temperature of the first surface is equal to T1 and temperature of the second surface is equal to T2. So here just like same process, just like but here because infinite parallel planes means you can assume areas are same. Okay, so then here also you can take the first formula what was derived in previous slide, just like heat transfer by radiation between the two surfaces. So you can take first formula. This is the formula, you know, that Q1T is equal to 1 minus epsilon 1 by epsilon 1. So sigma T1 to the power of 4 minus T to the power of 4 area A1 by 1 by 1 minus epsilon 1 by epsilon 1 plus 1 by F12 U factor 1 minus epsilon 2 by and epsilon 2 into A1 by A2. So this one already derived this one. So here, so you know that here, uh, so view factor F12 between the two parallel plates separated by small distance, you know that F12 is equal to 1 and the areas A1 is equal to A2 is equal to A. So we can substitute these values in this form and we will get the final value. Okay. So you know that Q1T is equal to sigma T1 to the power of 4 minus T to the power of 4 into in place of A1 we can see we can take A. So because A1 is equal to A2 is equal to A, because these are the infinite parallel planes. So instead of A1 you can write to A. So next to 1 minus epsilon 1 by epsilon 1 means 1 by epsilon 1 minus 1. You can write like this one also. So here 1 minus 1 by epsilon 1 minus 1. So you know that F12 between the two parallel plates. So we already discussed this view factors in previous class also. You can refer that one. So F12 value is equal to 1. So you can substitute the value plus 1. Okay. So similarly 1 minus epsilon 2. 1 minus epsilon 2 by epsilon 2 means 1 by epsilon 2 minus 1. Okay. So this is epsilon. So here also, here minus 1, here also minus 1 plus 1. So minus 1 plus 1 will be cancelled. Then the final formula, just like you can see the final formula. So that is equal to Q12 is equal to sigma A into T1 to the power of 4 minus T to the power of 4 by 1 by epsilon 1 plus 1 by epsilon 2 plus 1. So this is the value. So this is the form minus 1. Okay. So this one is the formula. So if you want to find the radiation heat exchange between the two infinite parallel planes, then you can use this formula. So epsilon 1 and epsilon 1. So this is the formula. So we'll see one more case also, just like suppose just when the radiating bodies are concentric cylinders and spheres. So in case of cylindrical bodies and spherical bodies. So here also F12 is equal to value is equal to 1. Here just like U factor is equal to 1 by 1 minus epsilon 1 by epsilon 1 plus 1 1 minus epsilon 2 by epsilon 2 into A1 by A2. So here in case of place of areas uh, for concentric cylinders, area 1 by area 2 means R1 by R2. It means here in place of areas you can write the radiuses also. In case of concentric spheres, A1 by A2 is equal to R1 square by R2 square. Similar formula, same formulas we can use, but U factor you have to take, that is equal to 1, and a similar formula same. Okay. So if you substitute these values in the first formula, you will get the final formula for the radiation between the two concentric spheres or two concentric cylinders. Okay. So this is the concepts of radiation between the different surfaces. It means radiation between the two surfaces, and difference radiation between the one small body and the big enclosure, and the radiation between the two infinite parallel planes, and the radiation between the concentric spheres and concentric cylinders. These are the cases we discussed in this class. So thank you for the listening class. We'll see one few more just like conditions. Conditions means radiation between the different planes. So if you will see next class radiation between the two surfaces. You place one more shield between the two surfaces. What uh, how the just like radiation will be changed, we'll see next class also. Thank you for this class.
Like, share, and subscribe. Hit the bell icon for more updates.